So in this assignment, we will take a look at example 1.18 in the textbook, and we will solve it using the Stephen-Maxwell equation, and we will do it on Google Collaboratory Notebook. So let's take a look. So the first section of the code is just basically importing all the important packages for the code, such as numpy and scipy. Then I input all the initial conditions such as diffusion coefficient, D12, D13, D23, pressure, temperature, rate constant, gas constant, mole fractions of the three components at z equal to 0, delta, which is film thickness, concentration, and N1 gas. So in this problem, there are a few unknown quantities, such as mole fraction of the three components, Y1, Y2, and Y3, and total molar fluxes of the three components, N1, N2, and N3. So we have totally 6 unknown quantities. However, if we take a look at the equation right here, we will get a bootstrap condition where n2 is equal to negative n1, n3 is negative n1, and of course we know that y1 plus y2 plus y3 is always equal to 1. So we can rewrite y3 as 1 minus y1 minus y2. So what we've done is just basically reducing the total number of unknown quantities from 6 to 3. So now we only need to take care of y1, y2, and n1. So what I would do is to guess the first value of n1. So that's why I have the initial guess right here to start with. Okay, so next I have defined a function dy, and it is dependent on eta, y, and n1. So dy right here just basically the derivative of mole fraction of the first and second components with respect to the relative position, or eta. And this part right here is just is derived from the Stephen-Maxwell equation that we've done in class, and if I've done everything correctly, the results would be in the form of an array with two values, dy1 over d eta and dy2 over d eta. Next, I have defined another function called y underscore right, and it is dependent on n1, of course, because I keep changing the value of n1. Y is a variable. So y right here is the mole fraction of the first and second components, and it is the solution of the differential equation dy over d eta equal to 0, where eta goes from 0 to 1, and the initial values where eta equal to 0 is y10 and y20. In the textbook, we were given that the total molar flux of the first component is equal to the rate constant K times mole fraction of the first components, where Z equal to delta. So we can rewrite it as the molar fraction of the first component, where eta equal to 1, minus molar flux of the first component, and 1 divided by K would be 0. So the app 0 right here is basically represent this, and it's supposed to be 0. So the return value of this function would be, the closer it gets to 0, the better. And then we will solve for n1 right here. I will call the value of the new n1 is n's, and I use the roots function and solve for y underscore right equal to 0 with the initial guess is n1 underscore guess, and then I plug the new n1 into the equation, the differential equation, and solve it again. And finally, I made a graph right here for y1, y2, and y3. So if we take a look here, it makes sense because y1, which is the reactant, it started with 0.6 or 60 mole percent, and because it is a reactant, it is consumed over time, so the concentration would decrease, and the mole fraction would decrease, and y2 and y3, these two are products, so they are produced. Therefore, the mole fraction is increased. It is very important to make the right guess at the beginning because as I said right here, the Ab's error value is expected to be 0. So if I put, let's say if I choose the value of N1 guess is 100, for example, then the value for Ab's error would be -11, which is way too far from 0. Or if I chose 1,000, it would be -101, which is not reasonable at all. So it is very important to make sure that the value of N1 guess is close enough so that we can have the most realistic value to start with.